Okay, so welcome back. Just before we go on to actually do the Grasshopper definitions to draw the contour plots, what I wanted to do is just explain the logic behind how I'm going to generate the contour plot for the internal forces. So what we have here is obviously just an element. So every element goes between the start node, node A here, and the end node, node B. And we obviously have the values for the internal forces, so the axial force, shear force, and bending moment at those nodes. And what I want to do is I just want to generate a mesh in Grasshopper. So it's not a mesh that we're using for analysis. It's just for the purpose of displaying the contour plots. But in order to do that, I want to generate a series of quadrilaterals that are essentially representing the profile of each element. So in this case, it's a rectangular element, so the depth or the thickness is the dimension that I'm interested in. And I'm going to generate a series of points, and then I just need to reorder those points so that they're always in a consistent order that's compatible with completing that quadrilateral mesh within Grasshopper. So the x-axis is defined as the axis going along the length of the element, so between A and B. The z-axis is the axis coming out of the page, so this is the local axis system that we currently have, and then that means that the y-axis will be the cross product between those two. And so the points that I need to generate, the first is going to be at node A, but at minus 0.5 times the depth or the thickness in the y direction, so the vector defined by the y-axis. The second will also be at node A, but at 0.5 times the thickness, and then the next one will be at node B, but at minus 0.5 times the thickness, and then finally also at node B, but at 0.5 times the thickness. So the first number on each of these sets of numbers is the number corresponding to the order that I've generated the points in. So we have 0, 1, 2, and then 3. But the order that I want to give them to Grasshopper in to generate the quadrilateral mesh is given by the second number. So this is 0, 1, 2, 3. So you can see going anti-clockwise round, which is a common way to define elements. And I'm going to achieve that just with a weave component once we get onto the Grasshopper definition. Okay, so we're just picking up where we left off last time. So you can see I've got the plot the beam axis group of components here. And now we're just going to follow the logic that I outlined. So we want a series of values here. So these are just bringing in the beam depth or the thickness value. We're then going to have a panel. So what I want to do here is one of the points is at minus 0.5 times the thickness, and the next one is at 0.5 times the thickness. So we'll just do what we normally do and make that into multi-line data. Then I want a vector. So this is the vector that we are bringing through as the y-axis vector. So I'm just going to label it like that. And the final thing that I'm going to do is just introduce a magnification factor. So if we want to, for example, increase the thickness, because the thickness might be very small compared to the length of the beam, we might want to magnify that. So I'll just bring in a slider, and I'm going to have it vary between 0.1 and I think we'll go up to 10 in this case. And then I'm just going to label that slider as the thickness magnification factor, like so. Okay, so I want to just connect a value in here. So I'm bringing this across as our thickness. And obviously just noting this is in millimeters. So what I need to do is just zoom out, and the depth is what I'm going to bring across as a thickness in this case. So just to maintain, I don't really want loads of wires crossing here, so I'm actually going to hide that wire display, but obviously it will reappear if we select the elements like so. The y-axis will come from here, so this is going back to just the component group that we had for plotting the internal force diagrams. So I'm bringing across the y-axis from there, and then what I want to do is have a multiplication component, so just times, and into this I'm going to put my thickness. Then I'm going to put the y-axis component. Then I want my values, so obviously 0.5 or minus 0.5 and 0.5 times the thickness, and I'm just going to graph them to make sure that they're going to be processed as individual values essentially, rather than just as a list. And then the final one that I'll add in here is the thickness magnification, so I just need to generate an additional component for that. So we have that in there like so. So what this will do is it produces two sets of 8 points. So we had 8 elements in this case, and then those are the ones that we're going to be able to use to actually plot or generate the mesh for the contour plot. Okay, so what this is doing is it's generating the vectors we need, but obviously we do still need the points, and I'm going to allow the contour plot to be plotted either on the undeformed or the deformed shape. So what I want to do is bring in the elements, which is going to be this component back here. So I'll just have a line component here, and I'm going to group this and just label this as elements and bring it over from up here. And then obviously I want the start and the end point, so the ones corresponding with the node, so I'll bring in the endpoints like so. So now what I have is I obviously have the start and the end point, but I now want to move these by the appropriate vectors. So I'll bring in the move component, and we want 2 of those. So we have the start point as the geometry going in there, end point as the geometry going in there. And then from here, I want to bring across my vectors to move each of those. So just clearing up that mix up with the inputs. The next thing that I want to do is I want to basically, so in terms of the output of these, we still have a tree structure. So this is just sort of handling the data. So I'm actually going to use what's called an explode tree component. So what that will allow me to do is it allows me to take one branch basically of the tree, so in there, and then the other branch will be in here. So you can see, I hope already, that one of these branches is associated with the minus 0.5 times the thickness points. The other is associated with the plus 0.5 times the thickness points. So I can do the same for the end node down here. So again, the explode tree command coming in here. And then this is the point where I actually want to weave this information, as we were discussing just beforehand when I sort of explained the setup of this component grouping. So we'll bring in the weave component. So the first input here is a pattern, which we'll deal with in a second. And then these other components are stream components. So in terms of the components here, we're just going to run these across in the order that we generate them, like so. But then in terms of the pattern component, this is where effectively we're correcting and we're putting in the order that we want to display our quadrilaterals in. So for this one, I'll use a panel, and the order that I want them to appear in is 0, 2, 3, 1 compared to how we generated them. So that's effectively the first number on the explanation that I showed previously. Change that into multi-line data, and you can see just in here, this is the point that they're actually going to appear in after the weave component. So we'll just do that. So I have just brought the bifocals component down here. I've left it off at the moment, but if I show that, we can then just see the names of all of these components here. So if we look at the output from the weave component, we can see we've now really generated a list. And what we want to do that is obviously partition it into sets of 4 points. So I'll just get my partition list component, and the segment size in this case, we obviously want to make 4. So I can run that in there, and this is a little bit complicated, so again, we don't necessarily need to do this, but I'm just going to simplify the output from there. So that has the points that I need for the mesh generation, but obviously what I want to do, and we can see the points appearing over here, but what I want to do is I want to include the values that are then going to be used to inform the color of the mesh at those points. So we need to bring numbers across. These are just the values that we have at the start and the end node. So I'm just going to label these. So value at start node, and then also value at end node. And obviously we're going to zoom out, and we will get these from up here based on the gated output. So we want to take them directly from the gated output here. So that is the value at the start, and then this is the value at the end node. So in terms of the contour plot that we'll be plotting, it comes from whatever force or moment we've selected here. Okay, so we need to weave this information in the same way as we've done above for the points. But in order to do that, we also want to just check on our output. So our output is appropriate. So obviously at the start node, we want that at both of the points we've generated associated with the start node, and then at the end node similar. So that's why we're connecting that up like so. And the weave pattern is the same as we have above, so we can just bring that down. And again, what this should do, so it actually, we don't necessarily need to partition this list, but I'm just going to put that in case there had been anything going on with the data beforehand. So we will bring in our partition list component. If you are unsure about this at all, so what we could do is just flatten this, and then you can see that brings this out in a list rather than that structure that we had. So for the segment size, I'm going to set my integer, so 4 in that case. And again, we can see there's a little bit more complication than we necessarily need here. So I'm just going to simplify that. If we turn off the flatten, then actually you can see we get everything processed in the same way. But I'll maybe just leave the flatten on here so that we can see what's going on. Okay, So the final stage is going to be generating colors based on the values that we have, and then plotting these onto the mesh that we'll generate. Okay, so to plot the components, we're going to use what's known as a gradient component. So this is what that brings up here. If we right click on it, there's a series of presets. So very common, if we were doing finite element analysis, for example, we would probably use this rainbow preset down here. And what this will do is basically negative values will show in blue, positive values will show in red, and anything kind of in the middle just shows in a green or a yellowy color. On this component, we have the lower limit, the upper limit, and then the value. And essentially what this component does is it outputs color information. So what we would like to do is take the range that we're getting from here. So I'm just going to put in a number component here. I'm going to flatten the list going into this because I'm only really interested in things as a list. And then I'm going to use what's called a bounds component. So that basically allows me to find the minimum. So this is the list coming in, and then you can see this is the range. So in this case it was bending moment, so this is the range of values within that. What I want to do then is I can deconstruct that domain. So this is bringing that in, and I want to use my start value as the lowest value and then my end value as the upper value. And then into the colors, this is where I can feed the information that I've got from that partition list component. So what this will output is, if I just put a panel here for a second, so this generates RGB colors. So basically the first color out of 255 is the amount of red, second number is the amount of green, third number is the amount of blue. So I also then, so I've got all of that color information. So now I want to generate a mesh. So actually it's the construct mesh component that I need to use. So these are the vertices. So obviously in here, I'm going to feed in the points. But the faces, you can see this is quadrilaterals. So actually I can leave this as I want. And the nodes, or the points rather, are going in the order that I wanted. So the final, or almost the final step, is I can connect up the colors. And actually we can see already in Rhino over here, showing the preview plot, that the colors make sense based on the bending moment diagram that we had previously. So the final few steps are, we obviously want to apply some values on here. So in this case, I'm going to plot the values at the start node. So I want to bring them in as text or a string. So text component is the one we want there. And actually we're going to bring it in from the text component that we already had up here. So I can bring that across. Then it's the text tag that I'm interested in. So this is coming in as the text that I want to display. And then I also just want to add the location. So I'm going to add the location as the start node. So we can see we have the numbers being plotted like so. I'm just going to use a color swatch component. So that's just to set the color of the text, and I would like it to be black. So we'll just accept that component. So what we now have is these two components together. This obviously allows us to plot our diagram and include the numbers on that diagram. So I'm just going to group them and say this is the diagram and values. And so actually that is everything that we need to do in order to produce the contour plot. So I'm just going to group all of these elements and I'll just pull them down a little bit, but I'll label this as contour plot for the axial force. So that's Fx if we're in the cross-section axis system, shear force Vz, or bending moment, and this is obviously the one that we have plotted, or bending moment My. Just a note, so the thickness magnification factor, I had that turned on and I was quite zoomed in. So if I set that to 5, for example, we can see obviously it's massively zoomed in that case. I'm just going to go and deliberately set it to 1 here. So we can see then, so actually this seems to be kind of high. So I'm just going to double check on what might have gone on there. Okay, so what's gone on here, if I just look at the vector, we can see that the value for the y direction in that is quite high, so 125. And it was just because of the way that we generated it back here in the cross product component. And what I hadn't turned on here was the unitize, so basically to make the element length, or rather to make the vector length here 1. So if I change this boolean to true, then you can see now in our plot that is the actual depth or thickness that's been displayed. And obviously if I change the thickness magnification factor here, that allows me just to change that over there. So I'm just going to set it back for 1 just while we're displaying the final bits of information. So what I can obviously also do, so I'll get the diagrams and the values back up here, but I can go back to here, for example, and I can say actually I want to plot it on the deformed, so we can then just see that's appeared like so. Obviously rather exaggerated deformation here, so I'll maybe just put it back to the undeformed, and I can look at the axial force, which as we would expect is quite a boring plot. It's just 0 at every location. Occasionally that will show as minus or positive, just due to very slight rounding errors, but I can also plot my shear force, and you can see the shear force does sort of flash up a few different colors, so it's not perfect. Probably if we did a little bit of rounding here, that would resolve this issue. But what you can see is the actual value that we have is consistent all the way along. Okay, so to just try and resolve that rounding issue, so to make sure that the contours plot as we would expect, what we can do is we can use the round component. So if I do Control-Alt, and that gives the information, and then I do left mouse click, you can see that's just coming from the maths tab here, so it's one of the functions in there. So I'm going to look at the value, obviously at the start node we need, and I'll just bring in another round component to deal with that there. So what we can see is this then obviously generates the number. It also generates the floor and the ceiling. So I think we have an option here, or maybe not. Okay, so this is going to round, I think, to the nearest whole number, but let's just check what that's doing. So if we look at the number that's been outputted, yeah, so it's rounding effectively to the nearest integer. So providing you know that's a level that you're happy to round to, that's okay. So from here, I will just take that as input back into here, and then as input into here. I'm just going to move these components into the group like so, and I can just select them and right click now, and then just say add to group. And so now if we look at the output, you can see that's resolved the issue with the shading, but you clearly just need to be aware that it has rounded back with these components to the nearest integer value effectively. So the final one that I'll show is just the bending moment diagram, because I think that's probably the most illustrative. So we have the bending moment diagram here, the values as we would expect, and then the very last thing I'll do is I'll just turn the bifocals back on, have a little look over this component grouping here, so you can see how everything's been put together there. Okay, and I will see you for the final video where we will do contour plots of the normal stress distribution through the depth.